enter that start of class word we just talked about, and give me those green checks. I've got 3 green checks so far, so I just want to make sure it's working for everyone. Give me those green checks. There we go. Perfect. All right. So this is a reminder, Class Connect sessions are recorded and distributed for learning purposes listed here. As always, be respectful, appropriate, and participate, but don't share contact or social media info during class for your own security reasons. All right. So here we go. Here is our brain stretch for the morning. You can either, you can work on any of these. Obviously, do all of them if you know all of them. But I want to know, what's a chemical change? Does it mean substances stay the same or become different? Right? Use your whiteboard tools. You can circle your answers. Viscosity, which is a fluid's resistance to flowing, is that a physical or a chemical property? Think about when the viscosity of honey was changing. Did it change the identity of honey? And depending on that, is it a physical or chemical change? And then again, we're going to review this because we made a mistake yesterday, so we want to make sure we get it right today. The total quantity of matter and energy in the entire universe, is it always changing? Always the same? Remember, conservation. What does conservation mean? And then you can also tell me, what do you want to do after graduate? Perfect. Okay, so let's go ahead and take a look here. So Becca, you said, right, you're going to college. Chloe, you said you're going to go to beauty school, dye and cut for hair for a living. Awesome. I actually really need to get my hair cut. It's like, it's getting crazy. I have a neighbor who cuts hair, so I'm like, I need to go talk to her to get my hair cut. Isabel, you said after you graduate, you want to go to college, figure out a good career like biotech. Yes, biotech is definitely an awesome career. We've discussed that a few times. Something in the medical field. Excellent. Luis, FBI or the Air Force? I actually have a friend who works for the FBI, even though I'm technically not supposed to know that. Becca, you would like to be a nurse. Absolutely. That is definitely a great profession in the medical field as well. We've been talking a lot about medical field jobs. Let's see here. Becoming a nurse, physical sports therapy. Perfect. Yes, that's super useful. I broke my ankle last year, at the end of last year during Q3, I think. And so I had to go to therapy, and it was very helpful because it was a really bad ankle sprain. Let's see here. Go to community college, become an operating room nurse. That's super cool. I don't know if I could do that. I think I might be a little queasy. You want to be a kindergarten teacher? I love it. Entertainment business? Yes. Don't even know yet, though you should by now. No, you still have time. Still have time, right? Again, if you go to a 2-year college, that's a lot of time to figure out what you actually want to do. Try out for the WWE. That's super cool. Let's see here. Joining the military, awesome option. Finding a job, attending a college, attend a 2-year, 4-year medical school for dermatology. Yes, 10 to 13 years of fun. And I'm guessing, Nichelle, that's you because you love dermatology. Very cool. So chemical changes. Yes, chemical changes mean that we are making totally different substances. But remember, the total quantity of matter and energy in the universe is always the same. Conservation. I'm glad we were able to fix this mistake from yesterday. So that means that even when substances become different, the total amount of mass or atoms still stays the same. 70 years to think about it, junior, and military was your only choice. Well, that's good because in that case, you know what you're going to do. Viscosity, right, is a physical property because even though you change the runniness of honey in the lab from yesterday, did the actual identity of honey change? Tell me in the chat box. Even if you change the viscosity of honey by heating it up, does its identity change? No. So if its identity doesn't change, then it must be a physical property. Perfect. Okay. So at this point, please make sure that you have your attendance check open again. It is 10% of your grade. Make sure you enter the start of class word. I give that out during the first 15 minutes. If you ever miss it, just leave it blank and fill in the end of class word at the end of class. But I do need green checks from a few of you. So still waiting on Albert, Alexis W., Alicia, Antonio, Chloe, Christian, and Jelly, Jorge, Caitlin, and Becca. Green checks. All right, looking good. So we are on day 5 out of 45 here. So we're starting a completely new unit. There are actually 11 units on only 10 weeks of class, so we're going to fly through them. So we are going to go ahead and start our new unit. Keep in mind, we do have optional support today. Remember, you can find those optional support links to Zoom, right? The Zoom links. You can find them either in the class plan on your course homepage, or you can also go directly to the plan tab. All right, go ahead and give me a rainbow if that makes sense. Rainbow if you understand how to find your Zoom link. Again, just click on the event either in your class plan or the plan tab, and then you can find that link. So if you need help on yesterday's lab, definitely come today, and I would love to help you out. It's a great way to do really well on the lab. How are you guys feeling about the lab from yesterday if you already did it? I graded a lot of them yesterday, so if you turned them in yesterday, I tried to get them all graded. How are we feeling about it? It looked like the grades were pretty awesome, so I want to know how you guys were feeling, though. Nichelle, feeling good? Awesome. Alexis, good. Yeah, so if you haven't done it yet, keep in mind that all the data is given to you. So it's a really easy lab to start us out with. Really easy lab to start us out with. Awesome, Jada. Yes, make sure you get it done today. So I will be entering zeros at the end of today because we do have an analysis tomorrow, which is our next big assignment. So I try to zero them out before our next big assignments. Okay. So keep in mind here, again, currently we only have the 1D lab. And so this 1D lab is worth 65%. So once I zero out your labs today, you will see your grade drop a whole bunch if you haven't done it yet. Oh, no. Yeah, remember, it always shows that you have an F until I actually finish grading it. And I don't know why it automatically transferred to the gradebook. I think I fixed that. But for some reason, it automatically transferred yesterday. But I fixed it. But you should see it updated. Make sure you get Star 360 done by this Friday because remember, if you do well on Star 360, you have less required live sessions. So make sure to do your best. Go through it slowly. Don't rush through it, right? Take your time. It only takes about 30 minutes anyways for each of them. So take your time, go through it, do your best, okay? And don't forget, everything is in your grades tab. Love it. So we have been talking all about nature of matter. Oh my gosh, this is the wrong unit here. Sorry, we're going to be talking about the states of matter. So today we're going to talk about the states of matter. We're going to talk about how particles behave in the different states of matter, determine how heat moves when we change between the states of matter, which is like phase changes, and we'll define the kinetic theory of matter, which if you were with me last quarter, you should already be familiar with what the word kinetic means. All right, and here is our agenda over here on the right. So at this point, I would like you to go ahead and open up your notes. Open up your notes and give me a green check if you are able to get those working. Want to make sure everyone is on board with that. Green checks if you're able to get those working. Again, you can also take pictures if your computer can't handle having more than one thing open at one time. So feel free to take pictures, but still give me a green check when you're ready. If you're ever watching the recording, remember you can go to Content, Unit 2, scroll down, find 2A, or it's also in your Grades tab. Remember, Grades tab is the most important place in the course. Hi, Hallie, good to see you. All right, so let's go ahead and start this. Remember, just have your notes open and ready to go. I will be giving you all of the answers. So we're going to start out talking about the different states of matter. So what I want to know is in the chat box or on the board, how are water, ice, and steam different from each other? How are they the same? We did already touch on this, so you might already know the answers to this. But just brainstorm really quickly. What are some differences between ice, water, and steam? We can see some pictures right here. We've got some ice, we've got some steam, we've got some water. And how are they the same? Yes, they are all made up of H2O. Absolutely, Andric. Right? So they are made up of hydrogen, 2 hydrogens, and 1 oxygen. So made up of H2O, all of them. Yes, so they do seem to be physically different. Go ahead and describe how are they physically different. How does ice look compared to water, compared to steam, right? Physically different. Yeah, so what does it mean? What does it mean for something to be solid? Go ahead, describe that to me. Right, so we've got things that are hot. Which ones are hot? Tell me in the chat box. Which one's hot? Which one's, room temperature? And which one's cold? Yeah, so we've got ice is a solid, right? So we've got ice as a solid. Ice as a solid. We've got water as a liquid. And we've got steam as a gas. Perfect. And let's go ahead and talk about those temperatures again. Which of those is hot? Ice, water, or steam? Which of those is hot? Yes, exactly, Nichelle. The hot one is steam. Which one is cold? Which one is cold? Yes, ice is definitely much colder. And which one is room temperature then? Wrap it up, finish it up. Yes, just the liquid water, right? So taking a look at this, we're going to go ahead and break this down today and explain what's happening to make them physically seem different, even though they're all made up of the same stuff. Go ahead and give me an 8-ball if you understand where we're going with this today. Give me an 8-ball if you understand where we're going. Perfect. Okay. So defining the four states of matter. Matter is anything that's made up of atoms, has mass and volume. Remember, atoms themselves have mass and volume, so anything that has mass and volume is matter. Okay? Now, there are four different states of matter, and the way that we determine what state of matter it is based on its particle activity. So you can make some observations here, right? You can see solids are super rigid. They keep their shape. Liquids move around a little bit more. Gases are very chaotic, moving all over the place. And we're going to talk about plasma today, which is kind of a special one. All right. So go ahead in your notes, fill in the word atoms into the blank, and only the word atoms. You should only fill in what's in red. You have 30 seconds to give me a green check to let me know that you have done that. Go, go, go. Excellent. All right, I've got about 18 green checks so far, 36 of you. Remember, if we're not participating, I'll go ahead and move you to the check-in room just because it's very exhausting for me to have to go through the list every single time if someone's just walked away from their computer, because we know that happens. All right, go ahead, give me green checks. Shelby, Susan, Julian, Caitlin, waiting on green checks from David, Estella, Tuan. I know you just joined us, Tuan. Go ahead, open up your notes. We're filling in number 1, which is that everything is made up of atoms. Fill in the blank with the word atoms. And Alicia, green checks. All right, looks like I've got most of you. Let's go ahead and keep on moving. All right, so let's go ahead and actually break this down. So solids and liquids are a little bit different, right? Solids hold their shape, which means that they have definite volume and definite shape. Okay, so what this means is that their volume, when we talk about the word definite, we mean volume does not change and shape does not change. Go ahead and give me, go ahead and give me a sun if that makes sense. Okay, so definite, the word definite here means it does not change. All right, so volume does not change. Does not change. The amount of space it takes up doesn't change. Its shape doesn't change. So the reason for this is because particles have very little thermal energy, very little heat energy. So instead of just moving around, they're actually just kind of vibrating in place back and forth, right? Which is so small that you can't even see it, right? So if you think about, oh, I see Landon. So if you think about like your computer or your desk or something solid in front of you, if you were to look really closely at it with your naked eye, you would not be able to see those particles vibrating. It looks like it's completely still. But if you were to zoom in on an atomic level, it would have a little bit of energy and those particles would actually be shaking a little bit back and forth. All right. So this is, for example, ice or frozen water, right? The shape and volume of ice does not change. The shape and volume of ice does not change. Think about ice in your freezer. It stays the same shape. It has a definite shape. It stays the same volume. It takes up the same amount of space. It does not change. Go ahead, give me a thumbs up if that makes sense. Thumbs up if that makes sense. Perfect. Okay. Now, liquids, on the other hand, are a little bit different because liquids spread out. They do still have a definite volume, right? Because 1 cup of water will still be 1 cup of water. Frozen water with your liquid water, yes. But they have an indefinite shape. So the word indefinite, what do you think that means? If the word definite means that it does not change, what do you think the word indefinite means? Think about the prefix in. What does that often mean? Yeah, it does change. So indefinite shape means that it can change. Can change, right? So this makes sense because liquids will change shape to match the bottom of the container. How many of you have seen the liquid cats on like Instagram or Tumblr? Or, right, how many of you have ever seen that? So literally those cats are changing shape to match up with the bottom of the container, much like actual liquids, okay? So particles have more thermal energy in liquids, so they have more heat energy. So this means that they're moving a little bit faster and they can actually flow past each other. Is it really, David? So for example, olive oil keeps the same volume or amount, but it does change shape. So let's go ahead and take a look at this example here. So right here, I have half a cup of olive oil. Okay, half a cup of olive oil. Now, if you take a look at this glass and I pour it into this glass, do I still have half a cup of olive oil? Tell me in the chat box. Do I still have the same volume, still have half a cup? Yes, I do. Even though it changed shape, I still have the same half a cup of olive oil. The amount has not changed because you can't magically change the amount of olive oil you have by pouring it into a different container, right? However, can you see how it's changed shape and how it can flow? Thumbs up. Can you see how it's changed shape and can flow? It can move, right? It matches up with the bottom of its container. Thumbs up if that makes sense. Thank you. Thank you, Nichelle. Thank you, Luis. Thank you, Johnny's. Love it. Okay, so let's go ahead and talk about gases and plasma then. So gases move very randomly. All right, so gases are actually even more chaotic. They actually have indefinite volume and shape. So this means not only can they change shape, like you can see steam moving around, but they can actually change volume, which means that they can get bigger and spread out. Okay, which makes sense again, because if you think about steam, it moves away from the pot of water that you're boiling. It did, Landon. Yes, I know. A tiny amount stayed in there. But in theory, right? All right, so changing temperature or pressure changes the volume of a gas. We're going to take a look at an entire unit of this. But if you think about a balloon and you make a balloon really cold, what happens to it? Tell me in the chat box. When a balloon gets really cold, what happens to it? It deflates or shrivels, right? So you're actually changing the volume of gas. And so this gas is indefinite. Its shape can change. All right, go ahead and give me a cake if that makes sense. Give me a cake if that makes sense. Love it. All right, and so gases will actually spread out to take up the entire container, right? We talked about how liquids will spread out to the bottom of their container. Gases will actually spread out to the entire container, or if the container is not closed, they will spread out forever and ever and expand forever outside. They will escape. And the reason for this is because their particles have a lot of thermal energy, a lot of heat energy, so they're moving very fast. They can expand, they can escape. I'm going to go over that in a moment, Micaiah. We'll review that in our check for understanding. Can you go in the living room, please? Alexa, play Bubble Guppies on the Fire TV. All right, sorry about that, everyone. All right, so plasma, on the other hand, is a really cool one. So plasma is actually found in the sun, in the stars, in neon lights, and in lightning. It's actually the most common state of matter in our entire universe, which is kind of crazy to think about. But it's actually more common than you would think, even on Earth, because again, it's found in lightning. It's found in like neon lights, right? So these things are actually pretty common in Earth, and especially, I'm betting some of you have played with this before. What is this at the bottom? Smiley faces if you recognize this, or tell me what is the name of this. Yes, they're plasma balls. So it's in the name, but if you've ever played with a plasma ball, right, which is attracted to the electricity in your hands and it moves around, that is actually plasma. So what's actually happening is it's a gas that's been superheated to the point where the electrons can move freely. So gases, right, they're really hot. Plasma is even hotter. So it's been able to excite them so that the electrons actually move away from the gas, right? So it's a gaseous ionic form. Exactly, Nichelle. So because it's made up of ions, which means pluses and minuses, it's got positive and negative charges. This means that it can actually conduct electricity, hence why it's found in lightning and in plasma balls and in the sun, but it can also be controlled with electric charges, which is why we can control neon lights. Go ahead, give me a thumbs up if that's beginning to make sense, and then I'm going to show you a really awesome video that I don't want you to do at home. All right, so please don't do this at home. All right, love it. Here we go. I gave you a warning. Don't do this at home. Give me a green check when you finish watching this. All right, green checks if you finished watching it. All right, again, as I said, Vanessa, tell your parents that I said not to do this at home. I'm not ready to get in trouble for this. Oh, there will be many things, Junior, because chemistry is all about explosions. Cool. All right. So what did you see in this video? Go ahead. Tell me in the chat box what were some observations that you saw. Anytime we want to watch a video, we want to make observations, figure out what's going on. Tell me what was happening in that poor grape video. Grapes were dying, yes, but why were they? Yes, we saw sparks, we saw the grape go boom, we saw heat and electricity moving around, absolutely. And what did the guy say was happening? Why was that happening? Well, what's special about grapes? What is special about grapes that was able to happen? Yes, the microwaves are actually getting trapped in them. So remember, microwaves are a type of electromagnetic energy, right? They're a type of light energy. And so microwaves have energy, which means that if they get trapped in those grapes, do you think that's going to build up energy or lose energy? Tell me in the chat box. If we're trapping those microwaves, do you think energy is going to increase or decrease? Yeah, it's going to build up. And so as it builds up, right, the gases around there get superheated. And as they get superheated, electrons begin to move freely, and you can actually see the plasma. You can actually see the plasma. All right, go ahead, give me a thumbs up if that's beginning to make sense, right? It's pretty awesome, but you've actually seen plasma in your lifetime, and now you've actually seen a practical and fun application to it. But again, don't do this at home. Cool. All right, so here are the phases of matter, right? Solids, liquids, and gases. Solids hold their shape, hold their volume. Liquids hold their volume, but do change their shape. And gases are crazy chaotic. They just do whatever they want. They have no specific volume, no specific shape. They spread out to meet all. They spread out to fill their container. All right, go ahead, match these up for me. Let's make sure we understand these: liquid, gas, plasma, and solid. Definitions over here: electrons can move freely. Definite shape and volume, indefinite shape but definite volume, indefinite shape and volume. Remember, definite means it does not change, indefinite means it does. Go ahead, match those up. What do we got? All right, I see Janice, Nichelle, Jorge, Andrick, Micaiah on the board. I see Vanessa and, oh my gosh, so many, Noah and, all right, Antonio and Becca, excellent. Solids are the good boys, liquids are the rebels, and gases are the bad boys. And yes, exactly. And what would that make plasma? All right, looking good. Let me go ahead and shrink these down. We're going to go ahead and go over these answers. This will be number 2 in your notes, so make sure your notes are ready to go. Let me shrink this down. Looking good. Okay, let me grab my red tool here. We don't talk about plasma. Ooh, plasma's been disowned. All right, so liquids. Yes, liquids have indefinite shape, but definite volume, right? The amount of liquid doesn't change, but its shape does, right? It can move around, it can flow. Gases are really chaotic, so they have both indefinite shape and indefinite volume. Plasma, those electrons can move freely, and solids are the good boys of our society, right? So they have definite shape and volume. They don't change their shape. They don't change their volume. This is number 2 in your notes. You have 45 seconds to give me green checks to let me know that you have completed it or taken a picture. Sorry, I'm clearing out your old green checks, so give me new green checks. Go, go, go. Okay, sorry. So waiting on Tuan and Estella and Hallie, Jarrett, Julian, and Susan. Green checks. All right, here we go. Moving on, everyone. All right, so now we're going to go ahead and talk about how we can change between those different states of matter. And these are what are called phase changes, okay? So what I want you to think about is, let's do a quick brainstorm. Where is heat going when water is being boiled into steam? Tell me, where is the heat going? Is it going into the water or away from the water? Think about, you put it on the stove, where is the heat going? Is it going into our water to heat it up, or is it escaping from our water? What do you think? Tell me in the chat box. Awesome. I see Junior got an answer for me. I see Andrick typing. I see Alexis typing. L typing. So we're focusing right here, right? We're just focusing on this part right here. Where's heat going? Is it going into the water or away from the water? Think about, if you're trying to heat the water up, is energy going into it to heat it up or escaping from it to heat it up? What makes more sense? Yeah, it's going into the water, actually. So we actually have energy going into the water, all right, in order to heat it up, right? We need to actually get it hotter, right? So we need to give it more energy. Go ahead, give me a thumbs up if that makes sense. So heat goes into it. Sorry, heat energy goes in. Heat energy goes in to get it moving faster and hotter. Awesome. Now, what do you think about when water is being frozen into ice? Are we adding heat in order to freeze ice, or are we removing heat in order to freeze it? Where's the heat going? Is it going in or out? Yeah, we need to remove the ice. And so where is the heat going? Is it going into the ice or out of the ice if we're removing it? Yes, it's going out. Exactly. So this time heat is actually escaping or leaving, right? So heat is coming out. Heat energy comes out to slow it down and make it move and make it colder. Excellent. All right, so that's going to help us figure out what's going on here. Okay, so when we change matter between the different states of matter, okay, when we change between them, which is called a phase change, thermal or heat energy is absorbed or released, depending on what's happening. So there are 2 different processes. The first is endothermic and the second is exothermic. So thermic means heat, and endo tells us what that heat is doing. So endo actually means that heat enters. So in this case, heat enters. Go ahead, give me a thumbs up if that makes sense. All right, you can actually see the prefix here. Endo looks a lot like the word enters. So heat enters it. Okay, which means thermal energy gets absorbed by that substance, like by the water in our pot, all right? And it increases its temperature, and this allows it to get hotter, allows it to change phases to the warmer ones, right? So that could melt it into water, or that could evaporate it into gas, into steam. So melting and evaporation, those are endothermic processes. Exothermic processes, on the other hand, if endo means enters, what do you think exo means? What's the heat doing for exothermic processes? If endo means enters, what do you think exo means? Yeah, it means that heat exits, okay? So in this case, thermal energy, heat energy gets released by the substance or removed from it, right? You take heat away from it, and so it decreases its temperature and you go the opposite direction. You get colder, right? So this is like freezing water into ice or condensation, going from a gas colder into liquid water. All right, this is number 3 in your notes. Give me a green check when you have it saved. You have 30 seconds. Fill in the first blank with the word enters, the second blank with the word. All right, 21 green checks so far. Still waiting on 14 of you. Thank you. Waiting on Antonio. Thank you. Waiting on Tuan, Chloe, Chris, Christian, Emily, Hallie, Julian, green checks. Perfect. All right, everyone. So let's go ahead and take a look at an example. So the first example is condensation. How many of you have ever had a cold glass of water? You've put it outside and it left like a ring of water on the table, or you could see all the water gathering on the outside of the glass. How many of you have ever experienced that? Yes or no? Tell me in the chat box. How many of you have ever experienced that? Yeah, absolutely. So this is what is called condensation. So what's happening is the gas around the water, the liquid water gas around the bottle is becoming so cold on the water bottle that it actually turns back into a liquid. So it goes from a gas to a liquid. So tell me, how is temperature changing? Okay, if we're going from a gas, all right, which is on the outside, to a liquid, is liquid going to be colder or warmer than the gas? Think about steam versus liquid water. Yeah, it's actually getting colder, right? That's why this happens when the bottle's really, really cold, right? So temperature is actually getting colder. All right, so if it's getting colder, do you think that thermal energy is being absorbed by that gaseous water, or is it being released? If it's getting colder, do you think energy has to be absorbed by the gas to get colder or released by the gas to get colder? Think about what that energy does. Okay, so absorbing heat means it's absorbing energy, which means it gets faster. So in this case, if it's getting colder, yes, exactly, Johnny. So you actually need to release energy. So in this case, it's releasing energy in order to cool down, in order to slow down. So that being said, what happens to the speed of the particles? If it's releasing energy, if it's losing energy, think about yourself. When you lose energy, what happens to your speed? I told you the answer, so we should know this one. Yeah, they're going to slow down, absolutely. So they get slower. And in this case, if we're releasing energy, is that endothermic heat enters or exothermic heat exits? Is that endothermic heat enters or exothermic heat exits? Yes, it's going to be exothermic heat is actually exiting. Awesome. So I'm going to go ahead and go through these really fast because we still have one more topic to go through and I'm almost out of time. But vaporization is the opposite, right? Condensation was gas to liquid. Vaporization is liquid to gas. This happens when you boil things or evaporation happens. So temperature gets hotter, thermal energy gets absorbed, the particles get faster. And so this is endothermic. Heat is entering it. Heat is making it faster. Melting is going to also be endothermic because, again, the heat is getting entered into the ice to make it faster, to make it hotter, right? It gets hotter, thermal energy is absorbed, they get faster, so this is actually also endothermic. Endothermic. Thumbs up if that makes sense, everyone. I know I'm flying through them, but I want to make sure we get through everything today. Thumbs up. Perfect. Now, freezing is the opposite of melting. So that's a liquid to solid. So this one's going to be exothermic then. It does the opposite. So the temperature decreases, energy gets released, particles are slower. Since heat is exiting, that's exothermic. And these last two right here are super cool. So deposition is when you get frost on leaves. How many of you have ever seen that? Right? You might not see it as much in California, but it does occasionally happen. Yeah, so frost is when it gets so cold at night that gaseous water actually completely turns into solid directly. So it totally skips the liquid phase. So in this case, it gets really, really cold, right? So this gets cold. And so this means that energy is being released to get super cold. And so it gets really slow. And in this case, what do you think? Is it endo or exothermic if heat is being released? Heat is it entering or exiting? Endo or exo? What do you think? Tell me in the chat box. Yes, you'll see it on grass. You'll see it on leaves, right? So heat gets released really fast, and so it's exothermic for exiting. Yes, sublimation is the opposite. Sublimation is if you've ever used dry ice. How many of you have ever seen this? Right, those blocks, you can get them in the grocery store once you turn 18. Or you could get them anytime food is packaged and mailed to you, right? So in this case, it's going directly from a solid to a gas. And so the temperature increases so fast because thermal energy is absorbed. The particles start moving really, really fast. And so this is endothermic. It has to absorb energy, get energy in order to move faster. All right, so really quickly, match these up for me. Think about, is energy being absorbed? Is temperature increasing? Are they faster and therefore endothermic? Or is thermal energy released? Temperature is decreasing, slower particles, and exothermic. So think about the second phase. Is it hotter or colder, basically? The second phase, think about, is it hotter or colder? Go, go, go. All right, looking good. I'm going to go ahead, pause your tools here. Let's go over these really fast. All right, so gas to a liquid, right? Liquid means that it's getting colder. Liquids are colder than gas. And so if they're getting colder, that's exothermic. Sublimation, right, means that it's getting hotter, right? Gases are much hotter, so that's endothermic. Vaporization means it's also getting hotter because we're ending with a gas. Deposition, right, is when we get things like frost, so it's getting much colder. So that's going to also be exothermic, releasing energy, getting colder. Melting is going to mean that thermal energy gets absorbed to make it faster into a liquid. Freezing is the opposite, it gets colder. Awesome, this is number 4. You guys have 60 seconds to do this and then give me a green check. And then we're almost done. I know we're out of time here, but we need to finish up our last notes. Go quickly. All right, awesome. The last thing we need to talk about, everyone, is the kinetic theory of matter. Remember, what does the word kinetic mean? If you were with me last quarter, what does the word kinetic mean? Think about kinetic friction, kinetic energy, right? What does the kinetic theory of matter mean? What does kinetic mean? Yes, exactly. It means motion. So the kinetic theory of matter means that things are in motion. Okay, no worries, Andrick. Make sure you just open it up again, and it should have saved all of your questions, hopefully, okay? If not, it'll be in the recording once that gets uploaded. All right, so atoms and matter are in constant motion and have thermal energy. Even in really cold things, remember, atoms still have a little bit of motion. They're just vibrating back and forth, okay? So what this means is that when particles collide with each other, they don't delete or create energy. Instead, remember, energy is just transferred, kind of like billiard balls. Energy is conserved. It is saved. So let me go ahead and show this to you really quickly. I'm so sorry, guys. My daughter is very upset right now. So here we go. So let's go ahead and take a look at this really quick up on the board and take a look at this. All right. So if you take a look at these billiard balls right here. All right. So take a look right here at these billiard balls. Can you guys see that? Thumbs up if you can see that. All right, so remember, this white ball right here actually has a lot of energy when it gets hit. But what happens is when it hits the black ball, it actually transfers energy to the black ball to help the black ball move. And that white ball actually loses a bit of energy. But again, overall, the amount of energy is never created or destroyed. The quantity stays the same. It just transferred from the white ball to the black ball. Go ahead and give me a lightning bolt if that makes sense. Lightning bolt if that makes sense. It just transfers. Transfers. Awesome. All right. So this is number 5 in your notes. Fill in the first blank with the word motion, the second blank with the word transfer. You have 30 seconds, and then I'm going to give you your end of class word. Thank you for being patient as we wrap up class. Go, go, go. Yes. Waiting on green checks. Alicia, Andrick, Tuan, Chloe, Jada, David, Emily, Estella, Jarrett, Jorge, Julian, and Micaiah, Nichelle, Becca, Susan. Green checks. I know, I always have to wait for Flash to come out on Netflix, though. All right, looking good, everyone. So we talked about the different states of matter, how they can change what's happening to heat, and we talked about the motion of particles. I'm going to go ahead and wrap us up here. Make sure you submit your 2A notes. Andrick, have a great day. Go ahead, log out, everyone. I do have another class to go to and a daughter to go console because the world